Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. Now we will look at the roadway network file. Like I mentioned earlier, roadway network is a node link based line work representing the roadway, transit and aviation. So if you are looking to draw a roadway system, we will be using a node link structure. Even the aviation routes are drawn with a link node structure, almost exactly similar to roadway, but with a straight line. So roadway network might look like this. And if we zoom in, let's say there is one city here, the aviation lines looks like a straight line between the cities with a small travel time. And transit system is also drawn for most part as a roadway network first. Each link is assigned a mode ID which defines the modes the link is intended to serve. So this is an so what we will do is we will have a lot of important statements. I'm gonna point them out by number just to give some transition between important statements. So this is the first important statement, let's call it. So the first important statement is each link is assigned a mode ID which defines the models the link is intended to serve. So let's say this is a roadway network and is intended to serve private vehicles, cars, trucks. So we give one unique ID to this these links. So usually in Campo model, mode ID 30 is given to the roadway network of intended to be used by private vehicles and trucks and buses. Let's say this is a transit. Usually the mode ID, uh, I think 10 is reserved for aviation. I mean, it depends on how the model is developed. By no means this is a standard. It just depends on who has developed a model and what number they have chosen. So let's say I'm trying to build a transit system here for this link, and this link is only for transit, then I will assign this mode ID 50. A node is typically A node typically represents an intersection for arterial highways, a merge or a diverse location on the freeway. So second important statement. The second important statement is when we draw the roadway network and whenever the link crosses, usually there is a node. So a node is an intersection of arterial and highways. Also, when we are drawing a freeway and all the merges and diverges, there are nodes there. So merge and diverge points are donated by nodes. Nodes are also used to represent a change in geometry, like I mentioned earlier on the roadway network. So what node can also do is, let's say we want to draw a curve like this. So Transcad usually just draws a linear line. So what we do is we draw one node here, then one dummy node here, and dummy, and then dummy, and then dummy. So there are these are not called dummy nodes, these are actual nodes, but for the conversation and explanation, let's call them dummy nodes. So there are some dummy nodes or there are some nodes that are used specifically for change in direction of the links. Nodes are connected to each other through directional links. So like I mentioned earlier, if there is node 1, node 2, then nodes are connected to each other by drawing a link which are directional in nature. So let's say I draw the link from 1 to 2, then this is called AB topography. So the way links are drawn, so let's say I'm drawing from node 1 to node 2, then my AB will be this direction, and the opposite direction in terms of topography will be BA. Now if I want to declare this direction as the main direction, then I will assign this link ID 1. So by assigning a link ID 1, the direction of AB is chosen as the direction of the link. If I want the BA to be the direction, then I will assign this link ID -1. So by assigning a link ID -1, the direction is assigned based on BA. AB and BA are the way the links were drawn when the model was built. It's just the way of clicking on one node and moving towards another node. So in this case, I clicked on node 1 and moved toward nodes 2. That defines my AB. But if I want to have a one-way link like this, I will assign this node ID. Is this a link? There is a link ID. So I will assign this link direction ID as 1. If I want the BA to be my direction, then I will assign this link direction ID to be -1. And if this is a two-way link, then I will assign the link ID as 0. In this case, AB and BA will both be available. This is the third important thing of the directionality. This is very, very important to understand directionality. So in Roadway Network, we have discussed 3 important things so far. I probably should have done the same thing for TAZs. So let me go back, and since I have already put them in bullet points, so here is easy. So each bullet point was an important point separating from the previous one. In the TAZs also I have put the bullet point, so each bullet point is kind of an important characteristics and have a different relevance. That's why they are in a separate bullet point. It's not just to fill up the pages. They have some importance which is different from each other. And then we discuss the area type, which is a big topic in itself. In this roadway network, what I'm trying to do is I'm trying to split the important points into smaller kind of explainable parts. So the first important point was each link is assigned an ID. So each link is assigned an ID which defines the mode that is allowed to use that link. Then in the second one, nodes are typically drawn at an intersection, and sometimes they are drawn to change the direction of the roadway. And then third important point is how these directions are assigned. So the way links are drawn is called topographical direction. You get the point. And the way links are assigned the direction is by using 3 digits, either 1, -1 or 0. Now, 2 important characteristics of a link. This is the fourth important point. Now, the 2 important characteristics of a link are link flows and travel times. This is what we use in user equilibrium, system optimization, and many other things. So at the later stages, when we are looking at mode choice, when we are looking at traffic assignment, the most important characteristic of a link is link flow and travel time. So the most important is actually travel time. So what link flow does, it kind of defines the travel time. Link flow is also used for capacity. It's to see whether we are exceeding the capacity or not. However, the most important characteristic of a link is travel time, which is dependent on link flow. So we are also looking at link flow. At the end of all the travel demand modeling, what we are looking is for link flow. So link flow is the final output we are looking for in the travel demand model, and travel time is one of the characteristics that will get us there. So, besides the link flow, the other factors affecting travel time are free flow travel time, which is given by capacity, speed, free flow travel time is given by free flow speed. Link capacity, alpha and beta values of BPR function, and there are some others. So given the large number of links, manually assigning link attributes is impractical. Hence, all the links attribute are assigned based on VLOOKUP table. This is very, very important to understand, and I will call this point number 5 to 10 because it's such an important topic. Let's look at the this in more detail. So what I will do is, since this is such an important and it always causes error, I will use the red color here, and I will use the red color here to explain. So given the large number of links, manually assigning the link attributes is impractical. We have usually between tens of thousands of links. So these lookups, this lookup table provide free flow travel time or free flow speed, link capacity, alpha and beta values on the based on the roadway functional class and area type. So what we generally have is, for the entire TDM model, we have tens of thousands of links. Now each link has its own characteristics. Now we have, let's say 50,000 links. We have 50,000 links. What ideally we are supposed to do is we go and look at this one roadway somewhere, try to figure out what is the capacity, what is the free flow travel time, and all those things. However, it's impractical to go and calculate all these things by hand and then assign them. So what we typically do is we use a simple lookup table, which is given, one of the lookup table which with typical values are given here. So what we do is we just create one lookup table and figure out what is the functional class of this link and what is the area type in which this link is located. Based on these two information, functional class of the link and area type in which it's located, we try to guess what is the capacity, what is the speed, what is the alpha and beta of that link. So in the TDM model, we do not go and manually figure out all the parameters that are needed. So let me write it. So travel time is a function of flow, like we have seen it many times. Travel time is T naught plus T naught into 1 plus alpha volume divided by capacity to the power beta. So ideally we need to go and figure out alpha and beta for all of the network, and then T naught is free flow travel time, for which we need free flow speed. So ideally we need to go and figure out what is the speed limit on all those links, and speed limit is a good indication of free flow speed. But instead of using speed limit, which is a better indication, it's practically impossible to go and code all this let's say 10,000 to 50,000 links. So what we do is we just create a lookup table with lookup table divided into urban intense and rural here, and then we figure out what are the values of alpha, beta, and free flow speed. In this table we can also add the free flow speed somewhere, because that's one of the biggest estimation we do, free flow speed. So because TDM model is such a large model, there is a lot of approximation done, and this is one of the biggest approximation done in travel demand model. This is a major approximation in network coding, leading to major project issues which are later discussed in later sections, and we will cover it in future videos under the section calibration of travel demand model. So we will cover some of the importance of approximating this and what we actually need to do when we are working on project to handle these approximations. The typical values used for the roadway types are provided here. I kept saying I will go back and define what alpha and betas are. So those depends on the roadway type, and those are provided here. Usually the value of beta is chosen as 4 and alpha as 1.5, but yes, 1.5, but it depends on many things, and it depends on calibration. Also it changes from one travel demand model to another based on how the travel demand model is calibrating. So we try to keep it constant between different updates, but they may change. So the point here to note is alpha and beta are not just two random numbers or two constant numbers. They are dependent on roadway type, and they might actually change between one travel demand model to another travel demand model, and from one update to another update. So we will stop here, and so far we have covered out of 3 files. We have covered the TAZ files, roadway network. I think we have started the roadway network. We haven't covered it. In the next video, we will continue with connectors and centroid. This is another very important topic. I do not want to overload this video with a lot of information, so we will start covering connectors and centroid, which is a very important topic in the next video. Thank you. So in last video, we were looking at the type of files that are used in travel demand model, and we are looking at 3 different geography files. One is TAZ files, which we looked at a little bit closely. Then we were looking at a roadway network, which we will going to continue our discussion on. Let me move this and start drawing and then we will briefly look at transit network. So within the roadway network, we already looked at the capacity and how capacity and speeds are defined for the roadway network. They are based on a lookup table instead of manually assigned capacity and speed. One of the best way to assign speed would be to take the speed limit and do some approximation based on the speed limit. However, this is too labor intensive, and usually we just use one simple lookup table leading to certain errors, and we will discuss about those errors in detail in the calibration section, which is 3.5.3.1. So this is the calibration section where we will handle a lot of common issues that we need to know. So let's start this video with discussion of centroids and connectors. These are another very important aspect of travel demand models. So a centroid is a location within a TAZ or zone where all trips within the zones are assumed to be generated and ended. So let's say we are looking at an area. It's drawn here. I'll just use this drawing. So this is my centroid. A centroid is a location where we will assume all the trips within the development. Let's say there are some residential area here, some commercial area here, and some areas here. We will assume that this centroid is where all the trips within the TAZs are generated. We cannot go and code small area here, small area here, and small area here, and then try to draw the links between them, and that's way too detailed for the a city-wide or several city combined wide travel demand model. So what we do is we have the small TAZs. TAZs areas are already small because they are based on census tracts and they are small areas. So this is let's say small area. So we do not go and further distinguish between, okay, there are some apartments here and some apartments there. So this is a small area unit known as TAZ, like we discussed in previous videos. So this is important point one. This has a serious implications when it comes to calibration, and it causes some serious issues which we will discuss later. So centroid is assumed to be a location where all the trips are either originated or ended within the zone. So it's kind of representing the center point of the zone. The centroid is coded using a node at the location that represents the center location of all development within the TAZ. So centroid is nothing but a node. So centroid is a type of node, and this node is assigned a special ID to declare it as centroid. That's it. So a node is drawn and links are drawn, and the node is defined as centroid by assigning it a special ID. So centroids are connected to the roadway network through the Centroid connectors, all called CCs. So these are Centroid connectors. In short, we will call them CCs. In travel demand model world, they are called CCs. So centroids are connected to the outside roadway network. This is a roadway network, and they are connected through CCs, which are usually a straight line. There is no point in curving and drawing a CC, perfectly, because we can change the attributes just using the straight line. It's just a representation. This is second important point. This is a second approximation, and it plays a very big role in calibrating the travel demand model. So second important point under centroid and connectors to remember is centroids are connected to roadway network through centroid connectors as shown in figure. So CCs are coded with a very high capacity, like we see here 9999999. So a lot of nines, and it's a very high capacity so that even no matter what the demand it get distributed to the local roadway network. In most cases, CC can act as a sort route and pull the traffic off the roadway network. So this is important topic number 3. Let me explain it on the right hand side. So let's say this is my transportation system of the arterial, and let's say I have a CC like this. These two are my CCs, and let's say some vehicles want to go from this location to this location. So one of the sort routes to go from let me change color for making it better. So one of the sort routes could be like this, another route could be like this. However, one of the route can also pass through CC. So the thing to remember about CCs is they are not a special link. They are just a link node structure where Centroid is just a node and the CCs are just as normal link as the other links. They are just called Centroid and CCs, but in the traffic assignment stage and the mode choice stage, they act as normal node and link. So only for the trip generation and distribution they play a different role, but for the mode choice and traffic assignment they are just as normal as other roadway network. So another path would be to take this road. Now what this can do is this can unrealistically divert a lot of traffic through CCs, because CCs usually kind of are shortcut in the roadway network. So let's say somebody wants to go from this location and there are some areas here. So if the CCs are not there, the driver might have to go like this and take a right turn. But if the CCs are there, if they can go like this, take a right, go here, and then there are some roads here. So CCs in the TDM model can act very easily as a shortcut, and in the practical side of things, some of the alternate routes are pretty far and CCs do act as the shortcut. It's not just a theoretical concept. In most of the travel demand models, CCs mess up the model by acting as a shortcut. So to avoid that, CCs, what we do is we, we increase the free flow travel time of CC. So in most cases, CCs can act as sort route and pull traffic off the roadway network. In order to avoid this unrealistic traffic diversion onto CCs, a free a low free flow speed is assigned to CCs. By assigning a very low free flow speed, the travel time on CCs goes up, and that route is not likely to be taken. Now the question can be, why don't we assign like a very unrealistically high travel time? So our speed as almost 0. So let's say we assign a very small number as speed, and then travel time is extremely high, so people are not taking CCs as a shortcut. Then one of the implication would be sometimes if a link get congested, vehicles do divert through the arterials, and we will not be able to capture those diversions. So in order to have that behavior in, we do not artificially inflate the travel time to infinity. So one of the ways to counter this issue would be to set the CC travel time for CCs to infinity, or a very high number, and then nobody will take this route as a shortcut. Everyone will keep going. However, CCs are not only connecting this centroid to external areas. CCs generally also represent the smaller roads that are present within the TAZs, and if the external links are filled up in real life, the vehicles do divert through these arterials. So we want to capture those phenomena, so that's why CC is not set to artificially infinity. Otherwise, a link will always be filled up, and that will not be realistic, that CC is never filled up, and CC is only filled up with start and end trips, whereas the link is filled up 100%. So this is an important thing to remember. This plays a big role in calibration. So point number one, point number two, point number three, these three play a very big role in TDM calibration. Again, there are some approximation here, which I mentioned last video as 5 to 10. Those also play a very big role in the TDM calibration. So the topics we are discussing here is just laying the foundation for the use of the model and how the model is calibrated, validated, and how we get a better handle on the models. So again, a very, very important concept. I would request viewer to watch this part again and watch some of these parts again, because this is where most of the travel demand model calibration and most of the important aspects kicks in. Now, people may be wondering is TAZ is a separate file from the roadway network. So let's say I have a TAZ here, I have a TAZ here, I have a TAZ here. Like I mentioned, this is a TAZ file, which is a separate file than the link node structure of a roadway network. And let me draw the link node structure in red here. So I have a, let's say I have a roadway network connecting to this. Then my roadway network goes like this. And I have a TAZ here connecting to, these are my CCs. Now this green has nothing to do with the red. These are two different files. So now the next question is how the trips generated, which is a property of green. So number of trips generated, number of trips generated is based on socioeconomic data, which is a property of TAZ. So we know the number of trips generated and a lot of attributes about how the area looks like, which is shown in the green. However, we need to assign them into a separate file. It's not only a different layer, it's a separate file. In a separate file, which is represented in the red color here. So we want to assign the green attributes, number of trips generated or trip distribution. So number of trips generated and then OD table onto the roadway network. So the way this is done is each TAZ ID, let's say the TAZ ID for this green is 146. Let's say this green TAZ here has the ID 146. What we do is we just assign this Centroid ID as 146 and then externally match the volume or externally transfer the volume. So by assigning the exact same ID of the green to this Centroid, that's how the data is transferred between two layers. So it's very important to know that these two are two different things and they are kind of, the values are not like transferred through Transcat, they are transferred through, I mean, obviously it's transferred through Transcat, but through external files. They are not interrelated with each other. The green has nothing to do with the red in terms of coding and in terms of, programming and stuff. These two are two different files with two different properties doing two different things. So the way TAZ layer interacts with the roadway layer is through assigning the exact same ID of TAZ layer as the centroid, and whatever the property of TAZ is, we will externally match it with the centroid, and that's how the values are transferred. So this is another important aspect to remember about file handling. So this is important point number 4. It should be noted that TAZ layer and roadway layer are separate files, not only like separate, they are actually separate files. Data between TAZ layer and roadway layers are transferred by assigning Centroid ID to be exactly same as TAZ IDs. For example, total trips generated from TAZ with ID 43 are assigned to Centroid with ID 43. That's how they are transferred. By manually assigning whatever trip ID is with the Centroid ID. Now, if we are creating a Centroid and if the Centroid IDs are not matching, the number of trips generated will be wrong. So it is ensured that the Centroid ID with ID 43 lies within TAZ ID 43. Additionally, one TAZ has only one Centroid. That's another important point. So important. That's a kind of I would say 4 dash. One of the implication is we cannot have two centroids because each TAZ has its unique ID. So this is my TAZ with unique ID. Let's call it ID. Now we need to assign this ID to the centroid. So the centroid ID needs to match this ID. So the centroid ID must be equal to this ID. So we cannot have two centroids matching those IDs and then assigning the same number. So each TAZ has only one centroid. It's an implication of how the file handling works. The next file we have is transit network. Roadway links are assigned a mode ID that defines the mode of the link, like I mentioned earlier, and that is intended to serve. So some transit system, for example, local bus transit, share the roadway links are used by automobiles. In such cases, the links are assigned mode ID of the automobiles. So a simple mode ID would be mode number 30. Mode number 30 is uh, assigned for like a private use vehicle. So if a bus is using this route, the mode ID for the link will still be 30 and then a bus route will be drawn. Some attributes of roadway network such as travel time can be used by both automobiles and transit system. So in this case, whatever the travel time on link is can be used by both automobile and transit system. Some transit system which has exclusive right of way, like I mentioned earlier, uh, light rail and heavy rail are coded onto the links with special mode IDs. This prevent automobiles from using these links and that are assigned exclusively for transit system. Transit network are very tricky to be played with. We usually run it as it is, and we try not to touch the transit network unless we have to. It's very tricky. So while working on TDM model, changes to roadway networks are made according to project needs. It should be noted that the changes to roadway networks such as splitting the links affect the transit route system. If a transit system coding is broken, then TDM would not run. This is a kind of a very big and very common issue. This issue is generally fixed before a model can be run and does not result in incorrect link output flow. So when a transit system is broken, it will throw an error and the model itself will not run. So we will know that we are doing something wrong. It will not lead in incorrect result. It's just a lot of work to fix the transit systems. So in this video, we have discussed the different file structure assumptions and uh, how different attributes are coded in the travel demand models. In the next videos, we will discuss how these are implemented, how the 4-step travel demand models are implemented in the travel demand model. So we will look at implementation of 4-step travel demand model within Transcad, or let's say within any MPO's travel demand model in the next video. Thank you for watching, and please, I would highly recommend if you are first timer to rewatch this video. It's very important video uh, that goes through the file structure and everything, and as a uh, travel demand forecaster, we need to know all those things before we go and try to implement it and try to calibrate and validate. So this is a very important video. Thank you so much, and we will see you next time.